Okay, so here we have another problem. We have a 20-kilogram block is placed on the top of a 4-meter long rough ramp that is inclined at 20 degrees to the floor. It is released from rest and allowed to slide down the ramp. When it reaches the floor at the base of that should be ramp, the block then slides along the rough, flat, horizontal surface as it slows to a stop. The coefficient of kinetic friction throughout the block's motion along the ramp and floor is 0.13. So we want to use the work energy considerations to find the speed of the block at the base of the ramp. Okay, so again, let's draw our scenario. So here's our floor, and I'm drawing our floor because part of our motion, at least for part B, will be when it is along the floor. So what we have is we have a ramp. So let's say here's my ramp. That is way more than 20 degrees. Okay, let's make this just a little bit more realistic. That's a little better. Okay, so it's 20 degrees. So this angle right here is 20 degrees. We have our block that is on this ramp. And this has some height. We don't know what that is. We do know that the length of this is 4 meters. And we know that the block has a mass. I'm not going to label the mass right now, but one of the things that we do want to remember or kind of notice in this problem is that there is a frictional force. So I'm going to say F, lowercase f. And one of the key ideas to remember about frictional force is that the work done by this frictional force is a non-conservative. So this is a non-conservative force. So I'm going to put W and C. And that changes our work energy equation just a little bit. So if you remember, what we saw in one of our equations is that work of a non-conservative force is equal to our change in mechanical energy. So if we think about that, I'm going to just rearrange this a little bit. If we rearrange this, we get work of our non-conservative force, which in this case is going to be our frictional force, is equal to ME final minus ME initial. And if I were to rearrange this equation so that there's no negative, this would be ME, our mechanical energy initial, plus our work of our non-conservative is equal to our mechanical energy final. Okay. So let's think about this scenario and let's identify what types of mechanical energy we have. So when we think about the block at the top of the ramp, because we're just talking about the length of the ramp, we just want to know what is the speed at the bottom of the ramp. So we were told that the block starts at rest. If it starts at rest, it has no kinetic energy. Does it have gravitational potential energy? Yes, it does, because it is some height above the ground. Does it have, let's see, what else are we looking for? Does it have spring energy? No, it has no spring force. So all we have right here is mgh plus our work. I'm going to go ahead and just put work due to friction so that we know that. And then finally, when it's at the bottom, if you think about that and we say that this is 0, what happens is that all that potential energy has turned into only kinetic energy. So we have 1/2 mv final squared, which makes sense because this was what we wanted to figure out. Now, one of the things that we do need to know is we do need to identify what the height of this triangle is. So we're going to have to use a little bit of trig. And if we think about this, this is opposite over hypotenuse. So this is going to be sine. And so if I were to plug this in for my height and solve for my height, so sine equals opposite over hypotenuse, rearrange my equation, what I actually end up getting, I'm going to go ahead and just leave some variables in. It's going to be mg. This is going to be 4 meters sine 20 degrees. So that is going to be my height. Now let's think about my work due to friction. Now remember, my force due to friction is going to be a little bit different because we do have an angle. So when we think about our force due to friction and we want to solve that, we need to make sure we plug in the correct equation. So what this is going to be is this is going to be mu Fn. Well, what's Fn? Well, if you think back to our equations where we have an object on a incline, it is going to be equal to, this is going to be m, let's see, it's going to be mg cosine theta. And let's go ahead and start plugging in this, and this is still 1/2 mv final squared. One of the things I do want to show is that notice that my masses all cancel out. So actually I don't have mass in this problem. So let's go ahead and plug in everything else, remembering that we are solving for v final. So let's go ahead and plug in all my variables. I'm going to go ahead and start over here because I know I'm going to need a lot of room. So G is gravitational potential energy times 4, I'm just going to say sine 20 degrees to find our height, plus mu, which is our constant, and that is going to be times 9.8 meters per second squared. And this is going to be cosine 20 degrees. This is going to be equal to 1/2 v, I don't know why I made that f so big, v final squared. And we want to rearrange and solve for our v final. And what we end up getting when we solve for our v final is that our v final is equal to 4.15 meters per second. And so that is going to be the speed when it is at the bottom of the block. Now, part B says, use this work energy idea to find the distance the block slides along the flat floor as it slows to a stop. So what we want to know is that if it starts here with a certain amount of energy, which we know it has kinetic energy and we know what that velocity is, we want to know how far does it go before it gets to v equals 0, knowing that friction is working against it. So if we think about this problem, and go ahead and move this up so I can have some more room. We still have a non-conservative force because friction is still working. So we're still dealing with this equation right here. Now, initially, we have kinetic energy. And our kinetic energy is going to be 1/2 mv final squared. And we still have our force due to friction. So we still have this right here, and our friction, if we're thinking about on this flat surface, it is 180 degrees from the direction at which my object is moving. So let's just go ahead and go mu mg cosine theta. And let's see, this is going to be equal to, well, if it stops and it's at a 0 point, there's actually no potential energy. So let's go ahead and solve and identify what we have here. So we have 1/2, the mass of our block. Oh, wait. Our masses cancel out. I love that. So 1/2, 4.15 meters per second squared plus mu times 9.8. Oh, this is our force. So this should actually be right here. I forgot something. So this is our mu Fn. So that's our force. And then we have d cosine theta, because what we have right here is d, which is what we're trying to find, and then cosine 180 degrees, because friction works in 180 degrees from the motion. So I forgot my distance, which is really important because that's what we're solving for. So we have our coefficient times our gravitational or our acceleration due to gravity because our mass is canceled out, and then distance, and then cosine theta. So if we solve for d, what we see is that the distance it will travel, let's go ahead and put this in the right color. the distance that it will travel, d, is actually equal to 6.77 meters. So it actually travels for a pretty good distance considering the fact that the ramp was 4 meters long. But again, the block has mass, and so we had some kinetic energy. And so to come to a stop, it's going to travel 6.77 meters. So there is that type of problem. Again, some important ideas that we covered was the idea that we have an object on an incline. And again, notice that I had to use a little bit of trig to figure out the height.